Marangoni convection. Here we have a stationary series of streak lines left from the mica flake tracer particles, and we bring a soldering iron up to the edge of the frame. The soldering iron imparts a temperature gradient on the fluid, which in turn gives a surface tension gradient, and the surface tension then plays tug of war and makes a convection happen, as you can see here by watching the tracer particles. This is sometimes referred to as thermocapillary flow as well. We can drive Marangoni convection simply from the heat from a flashlight. You need to know about Marangoni convection whether or not you're really interested in it, because this could drive unwanted artifact in a microgravity experiment, say by just shining video lights onto a diffusion experiment. Here we are directing the energy from the flashlight in the center of the water sheet, showing that you can incite Marangoni convection without having the presence of the frame. Thin film crystallizer. Here we have a thin sheet of sodium chloride solution and time-lapsed video showing the growth of sodium chloride crystals over about a period of a day. And the fluid mechanics and the kinetics of crystal growth here is restricted to 2 dimensions. These crystals have a resulting thickness of about 1/10 of a millimeter. Here we see another crystallizer, nucleating crystals. There's one area on the right-hand side of the wire that is a hot spot that consistently nucleates crystals time and time again. The sodium chloride solution came from the galley. Instead of a salt shaker on space station, we have a sodium chloride solution so we can squirt the salt water on our food, and it makes nice science experiments. Here the crystals you see are about 15 millimeters on an edge. And you have a combination of hexagonal plates and squares. Here it has evaporated to dryness, and you can see the same crystals. You can harvest the crystals by reaching in and pulling them out, and again they're about 1/10 of a millimeter thick. Here we are making a thin film out of protein. Now this film happens to be blueberry flavored, and you might suspiciously think it's jello, but nevertheless it is still protein. And it is interesting in terms of what you can do with films like this, which will harden with time. And here the film is being made. Most of the bubbles are being excluded by the drawing process. After this film hardened, we used it to suspend some droplets of sodium chloride solution, just as a demonstration for what you might be able to do with a protein film. If you had the right chemical constituents, you could use it to suspend little chemical reactors where you could have diffusion reactions going on between the film and these reactors. And here we're just showing a time lapse of sodium chloride crystals growing while they're suspended by this protein film. This film has sufficient integrity that you can snip it out of the frame with a pair of scissors, and then you can put it in a baggie and you can bring it back home if you like. And again, this is representing what you could possibly do with films made of proteins or other materials in a weightless environment. Here is a two-dimensional sheet made of sugar solution, and it became saturated with time and started to grow these needle-like sugar crystals, and over a period of about a week and a half the crystals grew and filled in the whole frame. Nucleate boiling. Here we use a soldering iron to instigate nucleate boiling within a sheet of water. These sheets have to be a little bit thicker. They're about 4 millimeters thick. And when the tip of the soldering iron is submerged into the sheet, it immediately drives rather violent convection, as you can see here. Bubbles will form on the tip of the soldering iron, and they will be whisked away by this convection and leave a free surface for more water to be in contact with the tip and make more bubbles. Here is the soldering iron submerged up into the barrel, which is about 15 millimeters in diameter, and this was to provide simpler geometry than the conical tip. And here you can see bubbles forming on the surface of the barrel. They expand, they move away, they are whisked from the surface, and new water moves into its place and is heated and forms more bubbles again. To first order, this doesn't look that much different than watching water boil on a pot sitting on your stove down on Earth. Here we're moving to more of a spherical geometry where the barrel of the soldering iron is wet with a spheroid of water, and we can watch over time as boiling is developed. And again, the bubbles move from the surface in the absence of gravity-driven buoyancy and gravity-driven convection due to other means, and they move around, expose the surface to new water, and you have boiling that does not look that much different than boiling in a pot on your stove.